This is 4.4 matrices and linear systems. I'm going to kind of cut this section down from what I did last year and just kind of talk about it instead of actually going through it. So hopefully this video doesn't take as long as the previous one. Okay, I want to talk about what a matrix is. So it's just a rectangular array of numbers. Basically, that's all it is. There's three matrices shown here, there's a matrix here, and there's a matrix here. So it's just putting a system into a rectangular array of numbers. We have what's called the order of a matrix. The order is always given as the row by the column. Okay, rows are horizontal, columns are those vertical. So however many horizontal there are times however many by however many columns there are. So a matrix with the same number of rows as columns is called a square matrix. You'll notice that if it has the exact same rows as it does columns, it'll end up being a square. So determine the order of each matrix. So the order is the row by the column. So this has 2 rows, and it has 3 columns. So this is a 2 by 3 matrix. Okay, it's not 6, it's not being multiplied, it's just saying 2 by 3. This is a 2 by 2 because there are 2 rows and 2 columns, so we would call that a square. Just for reference, that's a square matrix. And this one, however many rows there are, 1, 2, 3. Remember, it has to be rows first and then the columns, 1, 2. So that is a 3 by 2. All right, a matrix derived from a system of linear equations, that is, a matrix formed from a system of linear equations, is called an augmented matrix. Now the matrix formed just from the coefficients, not the constants, so not anything after the equal sign, just the coefficients, the numbers in front of the letters, is called the coefficient matrix. All right, so if we're starting with a system of linear equations, and we're trying to put it into a coefficient matrix, I don't want the constants, so ignore those for now, cover them up with your hand. I just want to put the coefficients in a matrix, in a rectangular array of numbers. So I just go across. I start from the first row. There's a 1 in front of the x, so the coefficient there is 1. Always look at the sign in front, so that'd be a -4, and then a 3. Notice I'm not putting the letters in my matrix. Matrices don't have letters. They're an array of numbers, not letters. Then go to the next row and do these coefficients. So -1, +3, and -1. And lastly, I have 2. Nothing for the y, so I put a 0. And -4 on the z, so I put a -4. That's the coefficient. Let's look at the augmented. What would the augmented look like? Well, the exact same thing. It's this coefficients. But then I put this dotted line here showing that's the equal sign. And then I put what it's equal to. So 5, -3, and 6. So a matrix is just displaying a system in a new way. Instead of using letters, we're just going to use the coefficients. And understand that this first column, these are my x's, these are my y's, and these are my z's. And then, of course, over here I'd have the equal sign and my constants. All right, form the coefficient matrix and the augmented matrix for each system. So we'll do one together. If this is my system, notice I only have an x and a y, and I'm only going to have 2 rows here. So the coefficient matrix is going to have 2 rows and 2 columns, an x and a y column. And I'm going to fill in just the coefficients. So the numbers in front of my variables are -1 and +5. Then I have a 7 and a -2. Okay, next is the augmented, so copy down exactly the coefficient. -1, 5, 7, and -2, but then I have this dotted line here showing the equal sign, and I need to put 2 in the first row and -6 in the second row. And I would like you to please do part B. Okay, check your answer with mine. On the coefficient matrix, make sure you have a 0 for the y value in the middle row and a 0 for the z value in third row. And the augmented matrix, make sure you have this dotted line represent the equal sign. Otherwise, it's like you have an x, a y, a z, and then maybe another variable like, I don't know, w. Okay, but it's not a variable there. That's a constant. That's a number. So make sure you have the dotted line, and then 1, -3, and 4. Now let's work our way backwards. Let's go from a matrix into a system of linear equations. So I know that each column is a variable. I have an equal sign, and then I know I'm going to have my constant numbers. So I have a 2 in the x position, a 0 in the y. I could put 0y or I can leave it blank. I have a -8 with the z equal to 1. I have a -1 on the x, a 1 on the y. It's a positive, so I'm going to put +1 and a positive z, and it equals 2. Then I have a 5 with the x, a -1y, so I'm going to put -y, and then a positive 7z equals 3. That's the system of linear equations, so it can go both ways. All right, and this is the part that I just kind of want to show you. I definitely need to introduce you into matrices because you're going to do a lot with them in Algebra 2. But what I don't want to do this year is solve systems using matrices. So last section you guys were solving this 3 by 3. And we can still solve it like we want to, but the book goes into talking about how you can put them into a matrix. Okay, you can take the system and put it into a augmented matrix, solve the matrix, and then back substitute, which I like our idea of just solving the system, not having to put it into a matrix. So let's just talk about those row operations to refresh your memory, and it won't be tested over. However, you do want to pay attention during this part because it will help you solve systems, okay? So let's say we have an original matrix. We can still do one of our row operations, that's interchange. Okay, so you could interchange the row 2 with row 1. They switch spots. So this got bumped down and this one got bumped up into our new equivalent matrix. All right, and the next row operation, remember we can always multiply a row by a number. This is saying take row 1 and multiply it by a half. So what it did was it took 1/2 and it distributed it to all of row 1, kind of like we do in systems. So 1/2 times 2 is 1, then you get -2, 1/2 times 6 is 3, and 1/2 times -2 is -1. And everything else stayed the same. And the third row operation, remember that we can do, is we can manipulate a row. So like take row 1 and multiply it by -2. Right? But what's going to change is row 3. When you add it to row 3, that's the only one changing. It's not like row 1 stays being multiplied by -2. You're just changing it for a second, like we do when we solve systems. Okay, so let's look at what they did. They took -2 times row 1, and they distributed it. If they were to do that, they would get a -2, a -4, an 8, and a negative 6. They took that and they added it with row 3. Row 3 says 2, 1, 5, and negative 2. When you add those, what are we getting? Well, the 2's 0 out. That's my new row 3. Remember, I'm adding it with row 3. Negative 4 plus 1. That's a negative 3. So I put it in for my new position. 8 plus 5 is 13. And negative 6 plus a negative 2 would be negative 8. See how I got a new row 3? Row 2 stayed the same, and so did row 1. Okay, I multiplied it by negative 2 just for a moment, but it goes back to the original. Okay, so see how I solved that system there. I eliminated this because we want it in row echelon form, right? We want this to be 0. So I eliminated that, but everything else stayed the same. Just like you would do in solving this system. You have to eliminate that using this. Okay. The same rules still apply when you're solving equations. Okay, if you like the matrice method, put it into a matrice, and you still use those row operations. Nothing really changes except that a matrice, you're not writing X, Y, Z. You're just using the numbers. So some people like to use matrices. The same rules apply, that this would mean no solution, right? 0y equal to 11 is no solution, or 0 equals 11, or 0 equals 0 would be infinitely many. I think that's all I really want to talk about. If you're interested in using matrices to solve equations, come visit me and we can talk about performing these different row operations and practicing them. But really, guys, it's the exact same thing as you're doing, solving equations. All right, if you wanted to eliminate this 4x, you'd have to multiply the top by negative 4. That's what it says to do, and add it then with the second. Matrices, if you like them, come visit me. If you don't like them, if you want to do it the old-fashioned way with X, Y, and Z, let's just stick to that.